Thank you so much. Thank you so much for the introduction. As we all know, machine learning is basically everywhere in our lives, and everything we do, I'm sure even, I just woke up maybe 2 hours ago, and by now I have already used different systems that have taken advantage of different models to understand my speech and to show me results when I'm browsing the web. And all of these advances, they are due to a variety of reasons. There has been advances in the algorithms. There has been a lot of advances in new hardware design. But I think underneath all of them, the root cause that allowed all of this innovation to happen and that allowed everything to come together is the cloud. We have managed to gather all the data from everywhere and just dumped all of them into the cloud, where we essentially have close to unlimited storage. And if we have money, close to unlimited compute, and you can train any model on all the data that we have. And that allowed us to come up with all these models that we want to eventually deploy in a variety of devices, in our phones, in our computers, even in the edge or in big cloud data centers. And in the process, we have also learned how to build systems for to get these things done. We have different types of model that uses different machine learning paradigms. And we also have a lot of data that are stored in the cloud. And over the years, what we have learned is that we need to answer two key questions. The first one is, given all these data and given the model we want to train, what is the code that we want to run? Where in the cloud do we want to run? And the other question is, when do we want to run them and how we are actually going to run them? And these two questions boil down to sort of very roughly two layers in the typical software stacks that we see in the cloud. Application is given to a planning layer, and the planning layer comes up with the graph and the DAG and whatever and optimizes it. Then it's given to an execution layer, which figures out how to really execute that job on the data that we have. And eventually we finish running the job or finish the training, and then we have a model that we deploy. And of course, this is a extremely oversimplified figure with a lot of missing layers. And it's also not showing all the other things we have to deal with when we have multiple jobs that are competing. But the high level point stands. We have all the data, and we know to some extent how to make use of all the data to train our model. And there has been a lot of work to do it very efficiently. And again, just to recap, all of these things have been made possible because we can now capture all the data in the cloud, and then we sort of throw them to this or something similar to this software stack, and we process them. It turns out data cannot move as much as we have thought that it could move. There is massive data gravity. Data may not move because some data could be extremely private. It cannot move. Maybe there are some laws and regulations in different places throughout the world, and many different countries and continents are coming up with newer and more restrictive regulations. And it may also not be possible to move data because it's just too big, and we don't necessarily even need all the data. We may just want to get the insights from the data. So what we care about at the end of the day is not really big data, it's about big insights. And when we are in this position where data is stuck in many different silos, but we still want to do whatever we had been doing in the cloud when we could sort of move all the data because we got used to doing that. So we don't want to give up all the benefits that we got from training on all the data as much as possible to train all these gigantic models to get our work done. So to address that problem, a recent line of research that has appeared in the machine learning community is sort of called this federated learning. Here, the idea is that instead of having all your executors in black and the data in orange in the same cloud data center, they may be divided across many, many different places, and they are distributed over the wide area network. And typically, there is a centralized aggregator, and there are other models, but I'm going to ignore them for now. And when we want to train, The centralized aggregator has the entire model in sort of sends out this model to different workers. They run locally on the data they have. None of the actual data lives, but after the computation is finished, some updates are sent back to this cloud aggregator, and then everything is aggregated and an updated model is produced and then is sent back out for the next iteration of training. And over the course of last few years, two distinct kinds of federated learning paradigms have emerged. One is cross-silo federated learning, where data is distributed across multiple clouds. And I'm sure people from the systems community are aware of hybrid or multi-cloud analytics and learning. This is similar to that, or maybe perhaps exactly that, cross-silo federated learning. Each of the silo are far away from each other, but each of the silo is very powerful. They have a lot of compute. They're almost like an entire cloud. It just happens that data was distributed among them, and we want to train on all the data, but we can't really move all the data around. The other extreme paradigm is cross-device federated learning. So in this case, data resides in individual users' phone. This is even more extreme because in the earlier case, we could perhaps copy the data from the user to the closest cloud data center, to the closest silo. Here, we cannot even do that. Data resides on my phone, your browser. And whatever compute we need to do on the data, in the browser, in the phone, and only the updates can be sent back to the cloud for aggregation. And in both cases, it turns out the underlying network is the key difference, one of the main differences between cloud ML and federated machine learning or federated learning. The network that connects these distributed workers have much lower bandwidth than that we have in the cloud. It has much higher latency than that we have in the cloud. The topology can be asymmetric and very dynamic, changing over time. And given this new setup, over the course of last few years, we've been doing a lot of work in my lab across the entire stack, starting from the application layer to the planning layer to the execution layer, and in terms of also storage and data management. And today I'm going to focus on three such work. One is SOL, an execution layer for cross-silo federated learning. It also supports analytics. The other one is Oort, which is a cross-device federated learning system. And then I'm also going to spend some time talking about FedScale.ai. This is our open source project where we are trying to create a data set and benchmark along with a runtime system that is extensible and scalable so that machine learning researchers can easily write their algorithms on FedScale Runtime and then evaluate their algorithms on very large data sets. So let's get started with SOL. The goal of SOL when we started was to enable fast distributed computation over the WAN. So the setting is the cross-silo setting. We have data divided across many silos, and we want to compute whatever analytics jobs we have or learning jobs we have. And we found that the high latency of the WAN significantly impacts how much time we spend in actually working and how much time we spend not doing anything. So to give a quick overview of how things work in a typical distributed data analytics and learning framework, there is often a central coordinator, and there are a lot of workers, and typically these things would have been in the cloud. And coordinator has a lot of tasks because it's now trying to execute things. Workers pull for tasks, and tasks get launched. They do some work, and when they complete, they go back to the coordinator. They pull more work, and typically this idle period should be very small, and that is true in the cloud because the RTT within the cloud would be extremely low latency. But when we are coordinating over the cloud, it turns out that we spend often a lot more time just waiting for new work to arrive than doing any work. It depends on sort of how big the tasks are. If you are doing some tasks that are really small, then all this idling period actually adds up to significant overhead. So in our experiments, we found that for interactive analytics, just changing the latency of the network, the bandwidth and everything remained the same, the number of workers remained the same, just changing the latency of the links from 1 millisecond to 100 millisecond made average job completion time about 5 times worse. So high latency impact the runtime of the jobs that we run. And similarly, low bandwidth also affects. So in this case, we again have a coordinator which has a model, and we are doing training on the worker, and we are aggregating on the model. And in this case, a lot of idling period comes because either the aggregation is going on in the coordinator, or perhaps the bandwidth is really, really low, and it takes a while for the model to be uploaded and downloaded. And when we have many, many workers within a silo, and they're contending for this WAN bandwidth, what happens is that their CPUs just basically idle doing nothing while they are just all bottlenecking on the WAN bandwidth. And again, in this example, this is a set of machine learning jobs we tried out, and we changed the bandwidth from 10 gigabit per second a link to 1 gigabit per second. And the latency, number of worker, everything remained the same. The training jobs took 3 times longer to finish. The key thing here is that there has been a lot of work that, of course, notice this. WAN has a lot of impact, and they have tried to minimize bandwidth usage and so on. But what I want to highlight and what caught my attention was sort of both of these problems in the network. Of course, they cause network problems, but more importantly, they lead to compute idling. A lot of compute don't do anything just because we are bottlenecking on the network. Either we are waiting for new tasks to arrive, or we are waiting for data to be downloaded. So what Sol does, it redesigns or rethinks the control plane and the data plane of these distributed data processing frameworks, where in the control plane, instead of workers pulling work, it pushes work proactively. And in the data plane, workers waiting for download to finish and having their CPU idle, it decouples computation from communication so that computation tasks can do other work while communication tasks are downloading data. So in one slide, what we have done is that between the central coordinator and the worker, we have introduced an intermediate stage called the silo manager, where that allowed us to decouple this high latency, low bandwidth regime from the low latency, high bandwidth regime. So the central coordinator pushes tasks to the silo manager, and then workers pulls from the silo manager. And the figure on the right-hand side is what you typically have within the cloud, and the left-hand side is decoupled out, and where we do some proactive pushing to make sure that workers never block on tasks being absent from the silo manager. And even at the worker level, each of the worker, as I said, have been divided into computation task and communication task, or computation task and IO task, so that when we are bottlenecking on communication or IO, the computation tasks can or threads can do more work for other jobs that have computation work remaining, while some of the communication task is downloading data or uploading data. And there are many challenges, and I'm not going to go into any of them. They're described in the paper, but like some of the obvious ones are how many tasks we have to push and when we should push them. If we push too few, then we'll still end up with the underutilization problem. But if we push too many, then if there is a failure, recovery will take longer because we'll have to rebalance. There are other issues with complicated jobs with the dependencies, depending on what type of graph you ended up with that you want to run. If there is a failure, how do we rebalance? All of these things we discuss in the paper. So we deployed Sol across 10 EC2 data centers or clouds throughout the entire world. And we compared again Apache Spark on analytics benchmarks such as TPCDS and TPCH, and machine learning benchmarks like HighBench. And we found that 4 to 16 times improvement in cross-silo analytics and learning. At the same time, we also found that almost 2x improvement in overall utilization of the compute resources across all these sites. And these benefits come from both the improvements in the control plane and improvements in the data plane. So in this plot, we are running a bunch of TPC jobs, and job completion time of individual jobs are in the x-axis. Y is showing the CDF. And as you can see, the improvement over Spark in Sol comes in 2 steps. A big part of it comes from control plane benefit by pushing more tasks. The other part comes from data plane benefits by decoupling computation and communication. And anything that you can run on Spark actually would run on Sol, because it only changed the underlying execution layer, but it doesn't change any of the interfaces that people would use to write those jobs. So, and with recent advances in Spark, where people have create plugins to run PyTorch and TensorFlow on Spark, all of them can also in some way take advantage of this Sol execution engine. So that's a quick overview of cross-silo federated learning execution engine design, where we have to take advantage of the network. Let's change our focus to cross-device federated learning, where the challenges are even more. Of course, they're distributed over the WAN, but each of the devices have heterogeneous compute and capacity and heterogeneous data. And they also are can become available and unavailable at random points in time. They're controlled by the users, and there is basically no one in charge. So we wanted to design a system for cross-device federated learning, where we can take advantage of this enormous scale without having to worry about heterogeneity of data and all the problems they entail. And so we designed Oort. Again, this is a project led by my student Fan, and where we try to allow machine learning and federated learning developers to be able to express exactly how they want data to be selected. There are too many users that we can train on, but of course, we are not going to run on all of the users all the time. So what we do in federated learning is we sample and we pick only a small subset of users to participate in each round. And today, typically, these participants are selected at random, which basically leads to inefficient training, both due to statistical inefficiency because of non-IID data distribution, and also systems inefficiency because heterogeneous device capabilities lead to stragglers, which lead to longer rounds. So we both need more rounds, and each of the rounds become longer. Another key thing is with federated learning is that when we are trying to test a model, we test on some stale data that we had collected who knows when, and we can't really do any live testing of model. So we just have to rely on the stale data set for our testing. So this sort of slide gives a more concrete example. We ran or trained the MobileNet model on the open image data set in a federated learning setting, and for two different optimizers, FedYogi and FedProx. And the figure on the left is showing how many rounds it took for them to get to the final accuracy of roughly around 75%, which is shown on the figure on the right. And now I'm going to do an unfair comparison where I'm going to say that if we don't use federated learning, where we were only selecting 100 clients out of 14K every round, we select all 14K in every round all the time, and we do a centralized training like we would do in the cloud. How long does it take to finish? As you can see, it takes only 64 rounds, which is about 5 times less. And we also achieve about 10 to 12% higher accuracy using centralized training. So this is, of course, unfair that federated learning is using much less resource. But at the same time, this shows us there is a massive gap between these two operating regimes. And if we put sort of these points in a plot where x-axis is number of rounds taken for target accuracy and y-axis is average round duration, as I have mentioned already, because we are selecting participants at random, FedYogi or FedProx plus random selection leads to both more rounds and longer rounds. And so what Oort does in one slide is it tries to improve on both directions. On the statistical axis, it tries to increase efficiency by selecting high utility clients. And I will talk about how we select high utility clients and how do you decide something has high utility or some user. And then on the systems axis, it decreases the average round duration by prioritizing system sort of clients with high system utility, meaning clients that have faster devices. And of course, one question here is that, is it going to introduce any bias? But we do it after from a set of highly statistical utility clients. So they all have not exactly the same, but similar statistical utility. And among them, we select some of the higher speed clients. And so when we put all of this together for this particular example, MobileNet or OpenImage dataset, FedYogi is the same optimizer, just by replacing random selection with Oort selection, where Oort is trying to select a representative distribution from the underlying population. We improve in both directions and get much, much closer to centralized training. And some of the challenges here is how can we jointly consider statistical and system efficiency? There is a trade-off between speed and performance versus bias and fairness. So we provide a knob where the developer can decide how they want to weigh the two things and how they can sort of come up with a combined metric. We also sort of look into how we find, how can we find high utility clients at scale and avoid stale information and robustness. And just to give some quick insight into what is going on when we are trying to scale to so many clients is we have Oort that is trying to select from a pool of many, many clients. And in every round in this example, we'll be selecting only 3, but there are way too many available. All of them are heterogeneous and their utility can also change over time. So what Oort does, it selects a few in every round. And when it's trying to select, it tries to explore and exploit. So it exploits some already explored participants, but it also explores a few new participants. And it keeps doing that in every round. And in the process, while it's doing it, some of the clients that may have been selected too many times that become ineligible to make sure that Oort remains robust to someone introducing random data that looks good, but actually is not necessarily very good. And also, whatever we learn during exploration, after some time, they age out so that we don't rely on something that we have explored many, many rounds ago. I mean, just in case if their utility has changed by the time we come back to them. And there is a lot more details in the paper, but if we want to put everything together, then in this table, what it's showing is that FedYogi plus Oort selection, where we are trying to select a representative data set over FedYogi plus random data selection, which is select participants uniformly at random. The overall for OpenImage plus MobileNet model, we can get to the same target accuracy 3.3 times faster. And this improvement comes both from the statistical efficiency side and also in terms of selecting, sort of improving systems efficiency. And if we allow things to run until they converge, we can also achieve about 10% higher accuracy than whatever FedYogi could do with random. The numbers for FedProx with random and with Oort are similar, and they're in the paper. And this is not just for CV models. We have also tried out with NLP models and speech models. And in all of these cases, we have seen varying levels of improvement, but we have seen significant improvement across a lot of different workloads and data sets, both in terms of how fast we can get to sort of the target accuracy, but also how much higher accuracy can we achieve. And this part so far has been about training. But another thing that Oort does, which doesn't really come up too often when we talk about federated learning, is enabling federated testing. Say you are in the process of doing a training, either in a federated way or in your cloud. And we have to test the accuracy of the model to know that whether we have converged or whether we have reached the test accuracy or whether we have sort of have enough given whatever the developer is trying to do. It could be actual training, it could be for debugging. And in many cases, we may want to have a representative data set of the global distribution. And the global distribution, as you may know, it can change over time, and it's not always guaranteed that whatever someone collected 1 month ago, 1 day ago, 3 months ago, are still the same representative distribution. So if you want to test live, whatever the current performance of your model is, Oort can do online selection of participants and sample them using everything that I described before, so that it can select a set of participants that roughly follow the same distribution of the overall population distribution, And then you can test against sort of in almost real time how your model is likely to perform when you eventually deploy it. Today, for that, we basically have to train a model in the cloud, then we throw it out, then we collect some logs, then we understand and try to figure out where we are. Whereas using Oort, you can do almost live debugging of the model. And the second one here basically shows that if you found that for certain types of categories, your model is not behaving as expected or behaving poorly, you can also ask Oort to select samples of particular categories in your distribution, given a categorical distribution. Say you don't necessarily care about getting a representative distribution, you just want to understand for that type of input, how would your model behave? You can also instruct Oort and it will explore basically all of the clients and then give you a sample where that category is overrepresented and you can test against it. So together, Oort sort of enables us to do faster federated training and faster testing, but more importantly, Oort is a system that allows federated learning developers to sort of build on top of, and systems research to also do interesting systems research. And in the process of going through Oort, we found that to evaluate Oort, like the data sets that typically federated learning existing works use are too small, and from systems research point of view, too uninteresting. So we started collecting bigger data sets, and we also wanted to make sure that these data sets are not synthetic, but rather sort of they are collected and generated by actual users doing activities, so that we get some notion of sort of whatever happens in different types of scenarios in the real world. There are a few other challenges that we faced in the existing federated learning benchmarking sort of data sets. One is there is no systems details. The data sets are already small, and then where the data sets or the data should be located, what type of network they are running on, what type of device they would be running on, what type of cloud resources the aggregators have, the connectivity between the cloud and edge, and none of this information are available. And as I mentioned, that we also didn't have sort of very large scale data. And also we didn't really have any traces on in the existing benchmarks when the clients would become available and unavailable, because a mobile phone or a browser is not going to be available or online all the time. So what we had started, which started as part of actually sort of evaluating Oort, is collecting other sources of data where people have measured sort of the compute latency distribution of a variety of smartphones and their network connectivity, and also traces about sort of the behavior of a device plugging in and unplugging from the charging and so on. As you can see, for example, in the bottom right plot, there is a diurnal pattern you can see for individual devices sort of charging characteristics. So we collected these traces. And by the way, when I say collected, we didn't really collect them. They were collected by other sort of communities for different types of research. We brought all of them together and we collected ourselves from a variety of sources, the 17, 18 much larger data set that go up to maybe 2 million clients with up to sort of hundreds of millions of instances or examples they may have. And then we found several things. One is some of the existing sort of evaluation platforms that existed, without naming names, they are not very scalable. They worked out okay because they were running on really tiny data sets like Shakespeare, which actually doesn't even show up here because we just thought it's too small. Even though it's, I guess, very interesting and has been used significantly by a lot of machine learning works. But the point here is that like all these different systems that people have built, if you have, I guess, more than 10 clients per round or a bit more, then they don't even really scale out where you can emulate sort of hundreds or thousands or 10,000 clients per round. When you have 100 million clients, and perhaps maybe people would eventually want to take hundreds of clients or maybe even at least few thousands of clients per round. And so we build a runtime, which basically is a product of trying to generalize whatever we did in Oort, and we ended up with this FedScale Runtime, which allows us to scale to very large number of clients per round on the same amount of resources. And by the way, all of this works. This is an emulation platform, but FedScale Runtime also, we are building actual deployable version that can be deployed in Android and other types of devices to train sort of in the real world. The reason we rely on emulation on GPUs because we don't really have access to thousands of mobile devices. But having all of this together also showed us that for some data sets, the paper, like the longer version of the paper is on arXiv. So if you're interested, you can look up for some data sets, some of the well-known federated learning optimization algorithm that we know and that people say are better than others, the results may actually reverse because whatever assumptions they made when designing those algorithms, they may not hold in some of these data sets. So having a bigger data set and more interesting data set allows, or rather exposes a lot of deficiencies of existing works and allows one to explore further and design newer and more scalable algorithms. And just to give a quick summary, FedScale is sort of exposes this very simple API. I'm not going to go over all of them, but I wanted to highlight one thing. Like the entire Oort paper that I discussed is basically just implementing this select client function in the client manager of FedScale. And of course, there is algorithm and everything that we did in Oort, and FedScale itself started as trying to generalize Oort, but we believe that there needs a lot more work, but we are at a point where it allows us to quickly implement many different ideas and then evaluate them across a wide variety of workload at scale and find their pros and cons. To give another example of something that we haven't done, or we haven't proposed, is DPSGD, is a differentially private SGD implementation, which, excuse me, basically requires only a few lines of changes in the train function in FedScale, and we have managed to reproduce the results for the same data sets and for the same settings they have in their paper. So FedScale is not just allows one to come up with new algorithms, it also allows us to verify and reproduce results from many other existing work, which I would say seems too many from a systems researcher point of view, because in systems, things move slowly, whereas in machine learning, every day you get 10 new papers. So it's very hard to keep track of and compare things. So we believe that it's very important to be able to quickly try out all these different new algorithms and have apples to apples comparison on a variety of data sets that range from very large to very small and very heterogeneous to much less heterogeneity. So what we are trying to do with all of this thing is that we are trying to build a community effort that will be a set of data traces and system traces and set of models and scale factors for both cross-device and cross-silo federated learning and federated analytics. And I didn't really talk about federated analytics today, but I believe that federated analytics will also be another sort of key research direction, especially for the systems community, where you can think of federated analytics is a single iteration of federated learning. You may want to know what is the distribution of some attribute across the entire population. Say, I don't know, you have a company that has 1 billion clients and you want to understand how your app is behaving in that sort of metric. And instead of collecting all the log into the cloud and doing whatever, you should be able to do it instantly within few minutes or few hours live on all of the devices. So federated analytics not just allows this simple statistics, but it can actually allow much more complicated SQL queries, at least perhaps not the most complicated ones, depending on, especially in the cross-device setting, how much resources you have. But you can conceive that we can end up in this world where everything can be federated and distributed, and we don't have to collect any data in the cloud, or as little as possible. And another part of FedScale effort is the scalable runtime that I mentioned that allows us to implement algorithms quickly by plugging into the existing runtime. And then we are also building diverse backends and so that we can expose metrics that people would care about. So in conclusion, today I talked about Sol and Oort and FedScale, and they are in different layers of the federated learning and analytics stack. But there are many other things that we have been working on and we continue to work on that I hope you will eventually sort of take some time to look at. But I would conclude with sort of some parting thoughts. And I think as a systems researcher, there is, of course, a lot of opportunity to rethink software stacks that are network aware and heterogeneity aware and can adapt to changing conditions at this large scale and deal with massive uncertainty. And so it's a very ripe area for doing interesting systems and networking research. And we are doing a lot of it, but way too many research problems are hanging around. And the reason we are building FedScale, and we already have some of our friends and colleagues building on top of it, I personally believe, and of course I am biased, FedScale is a great vehicle to sort of extend it and do interesting systems research on top of it, where you can get a lot of data sets for free and you can quickly evaluate your ideas, but you can also sort of build up on top of it instead of wasting your time doing the basic work that we have already done. But there is also a side of the systems research that we want to do for federated learning is a service, not for us, but service to the machine learning community to create scalable evaluation platform that is very easy to use, where people can try out their algorithms on much larger data set that they're typically used to, and to make it really easy for them to quickly try and see how poorly or well they are performing before sort of they, I guess, put it on archive. I guess in machine learning, you just quickly put it on archive before doing anything else. But anyway, the high level idea is it should be very easy to use and it should be fast and scalable so people have the incentive. And we believe that as systems researcher, we can do much better in enabling or building such services for machine learning researchers so they can focus on the algorithm and not waste their time on setting up systems, which I believe we haven't really done a good job of so far, because most of my machine learning friends, they know a lot about GPU architectures and whatever, which should have never happened if we did a really great job. No, all of these things should have been abstracted away. So clearly we have failed with creating good abstraction and giving them good interfaces where they can get their things done without having to get their hands dirty with the details of clusters and networking and so on. So that's all. And I would like to conclude with thanking all of my students and friends and collaborators. The ones in orange are the ones whose work I have touched upon in this talk, especially my PhD students, Fan and Jia Chen and Sanjay and Jimmy Jie. They are sort of leading all of these efforts. And there's a lot of masters and undergrad students who have also been working. And of course, there's a lot of other researchers throughout the world who have been helping us with sort of doing all this work. With that, thank you again for inviting me and listening to this talk. And I'd be happy to answer any questions.
Great. Thanks a lot, Mosharaf, for the great talk. You visited like a lot of interesting topics during your slides. So Konstantin has a couple of questions in the chat. Let me start with the last one. So does FedScale automated runtime provide multi-node experiments? Yes. If so, what underlying protocols do you support? For example, is it TCP/IP, InfiniBand? Or...
Yeah, so right now we run over gRPC. It depends on like what type of binding gRPC would support. In theory, we can support all of them. So we try to abstract it away and not worry about it. But for the most part, it's running on TCP/IP right now because we are thinking of all this federated learning, especially the cross-device one. They would be running over the internet. And for the most part, many of them would be using TCP/IP. But you can potentially think that other sort of upcoming protocols can also be used. Say, I don't know, Quick maybe, other things.
Great. And then I have another question from Samuel Horvath from KAUST. Thanks for the great talk. Could you please comment on how privacy of clients is affected by Oort? And can you guarantee that there are no privacy leaks? Can you guarantee that Oort does not introduce any bias? It still optimizes the original objective?
This is, or these are a set of very good questions. So the first one is, can we guarantee there are no privacy leaks? We try to implement what is known in the existing work in terms of using differential privacy, but we haven't really done or contributed anything in terms of doing anything special on top of whatever is known in terms of differentially private federated learning. I know that there are some works that have shown in some interesting corner cases, there may be privacy leakage, but there is also sort of some other works, for example, very recently, a few weeks ago from Google, where they claim that there may be leakage, but to get that done, it will require massive coordination, which at least Google federated learning team thinks will be hard to do. But I actually, we haven't proved that there is no privacy leakage. So there may be a chance, but again, that sort of leads to another interesting work for someone to show that what type of privacy leakage there may be in Oort and how to address them. Similarly, for bias, we actually have recently found that I wouldn't say Oort introduces bias per se, but whatever bias Oort may have, it can actually be improved upon. For example, my student, Jia Chen Amber, she goes by Amber, she is working on a project where she has shown that in comparison to Q-Fed average, and I believe Virginia gave a talk earlier, she probably have has mentioned it, Oort has worse fairness between participants, but like we are working on and we are about to finish a work and submit hopefully, where we show that how to improve or rather mitigate these issues with biases in Oort. But there is a trade-off between improving bias versus improving time to accuracy versus achieving faster completion and so on. So it's a very complicated multi-way trade-off space. And again, that's why I was saying it's a very ripe area for research.
Yeah, after all, there is no free lunch, I guess, in our field. So I have another question. So from the Oort standpoint, do you have any evidence that it works on smaller scale experiments? Like if you don't have the population of devices in the multi-device setting, right? In the cross-device setting, sorry, of Google or of Facebook called Meta nowadays. Does it scale downwards? Like,
it does. I believe we haven't put them in the paper, but we have run all of the typical common data sets people use, like Feminist and Shakespeare. And in those cases, if I remember correctly, it also works as well.
Mm-hmm. And in terms of like the system traces, I've read like from your FedScale paper that you're based on the AI benchmark from ETH. Is that correct?
It's from an AI benchmark. I can't recall exactly where it was from, but right. It's this benchmark where they collected a lot of smartphones runtime on doing inference. And it's not perfect because inference is not exactly the same thing as training, and just multiplying by 2 doesn't really do it justice, because 2 times forward propagation may not be forward propagation plus backward propagation's time. But it's a proxy, and we are hoping, and this is something we have talked to many these bigger companies, whether they can, publish more data sets, because very few people have access to more accurate data sets. But this is another thing to be actively worked on. What we are trying to do, my student Sanjay, he is going through several Android devices that we have and getting all of these models and checking basically how long it takes to run some of these models that we have had in this benchmark, and what is the average iteration time on those particular types of devices. If you run on some amount of data for a particular model, how long, what does the distribution look like? How many milliseconds does it take? And it varies. And he's also identifying in the process that there are some data sets, or rather models in FedScale, they may be too large for some of the phones that we have, and for some of the newer phones, perhaps everything would be fine. So this is another thing we need to think of when we are designing models that we want to do a federated learning-based training. How can we actually throw it out? Not all models can run on all the possible devices, so that also creates the potential for bias in that some of the fonts may be too weak. And then if you never include them, you may lose out on whatever interesting data set they have. So this is another problem we are looking at, where we are trying to find that whether we should train on the like whatever the worst font can train on, or should we have this ensemble of models that are roughly generated from the same parent, but they have different levels of complexity and different levels of behavior, but then like aggregation could be trickier. So there's a lot of interesting work that we are looking at, and there is of course a lot of work that other people are looking at. I mean, there is basically at this point infinite number of federated learning papers. Every morning I get from Google Scholar like 10 new papers on federated learning. So
exactly. Yeah, exactly. And this gets exacerbated if you also take into account different, let's say, accelerators that are integrated nowadays in the system.
So one of the things Sanjay is doing, like when you want to train on a SOC, there are a couple of things you want to answer. One is like today's federated learning algorithms are very conservative in that the phone have to be plugged in. But it could be that if you could predict that if you start, it will take 1 hour. This phone is likely to be plugged in like 5 minutes, and you predicted that. And you can actually not give up that phone and their data, and you can actually get started. And then after 5 minutes, if it's still not plugged in and you mispredicted, then you can just, I don't know, throw away that 5 minutes worth of work. But we have trained model on at least some of these data sets that we have on the availability data sets. We can predict very well and sort of predicts when a phone is likely to be charged. So we can preemptively start training even when it's not being charged. Similarly, for it's not connected to Wi-Fi, but actually we can use this idea of, that's very old idea of delay tolerant network, where you can compute, then you wait for it to connect sometime in the future. You just know that it's not going to be connecting, I don't know, 1 month later. It's definitely going to be connect probably within 24 hours if it's an actively used phone. So there's a lot of opportunity. Similarly, on the device, on an SoC, we have all these different types of cores nowadays, weak cores and brawny cores and GPUs and AI engine. Each of them has different rates. So there's a lot of work to be done on the sort of mobile side runtime itself. And this is only talking about Android phones. No, there is these things could be deployed in browsers, in edge clusters, in other types of devices, video cameras, whatnot. So there is a lot of opportunity to innovate.
Definitely. And one last question before we close this session. It's again from Samuel. He asks if you could comment on how you estimate the statistical utility without users revealing their data.
So what we did is not really estimation, it's more like, I guess, an approximation. So we pick a client, then we train and we see the loss, and the bigger the loss, we assume that it has higher statistical utility. There has been some prior work that said, I mean, in the machine learning community at least, that it will work. We didn't really prove anything. Empirically, we saw it works very well. But again, if there are other better ways of determining statistical utility, that would be great as well.
This is going to be definitely more applicable in the area of federated analytics, as you said, because you might not have a loss function in place there.
Yeah. Yeah, thank you. Yeah, you're absolutely correct. Yeah, these are great questions, but I want to end with saying thank you so much. And there's a lot of interesting works in this world, especially for systems researchers. And I hope a lot of you will come join us in sort of trying to build scalable federated learning systems. Thank you.
Great. Thanks a lot for your time and your presentation, Mosharaf.
Bye-bye.
All right.